start the slideshow. So first we'll go through the task overview. After that, we'll see some of the basic concepts involved, which is the text preprocessing pipeline and the bag of words concept. Later on, we will see two machine learning algorithms, the decision tree and multilinear line space. We will also implement them. So if you have checked out the folder which I shared with you, then you can find one notebook labeled part 1, in which we'll see the code implementation and the subsequent results of what we get when we implement it. And at the end, we will go and implement deep learning. So we will have a look at word embeddings and how to construct them in TensorFlow. So this is a snapshot of the data set. So we have three rows over here. So the first one contains winner as a valued customer. So you can read this text and you can directly say that it is definitely a spam text. And even in the next one, you can see free entry in a weekly comp to win FA Cup final. So such types of text have been classified as spam. And the last one you can see that has been classified as ham. So ham is basically the class which indicates that it is not a spam message. And this is how the data set is organized, and we have around 5,000 SMSs with their corresponding labels. So you can ask that why is SMS spam detection so necessary in today's age? So most of the time we are communicating with each other using electronic media. So we are even using emails, chats, and SMSs have been in use since a very long time. And nowadays, spam propagation via text using electronic media has become very common. So you may have heard about email spam. So we always have a huge spam folder having a collection of emails which are really of no use. So Google Gmail, what it does is that it has an automated system to classify your email messages into spam or not spam. Similarly, we are going to see that how we are going to use machine learning techniques in order to classify SMS text into spam or not spam. So the first step is data preparation. So we cannot feed the text data directly to a machine learning algorithm. We have to do some pre-processing steps. And that's the thing. So we have we have a well-defined text preprocessing pipeline. So all these learning algorithms that we have, they require well-defined inputs and outputs. And we will convert the text that we have. So right now you saw those SMSs. So we are going to convert them into a vector of numbers. So all of those texts which are there, all of the words which are there in an SMS text, so each of those words will be converted into a number. And in that way, we are going to represent a sentence. And we need this modeling of text because your machine learning algorithms will not be able to work with simple raw text. So here you have the text preprocessing pipeline. So the first step which we have is lower casing. So lower casing helps us to minimize a lot of variations within the text. Then we have punctuation removal. So punctuation isn't really necessary in most of the cases, unless and until if you want to capture an exclamation or if you are working in some specific problem statement, then you may want to preserve certain punctuation marks. Otherwise, for regular usage, it is not necessary. After that, we go for tokenization. So in tokenization, what we do is we are going to split the sentence into each and every word. So a sentence will be, after tokenization, a sentence will be represented as a list of words. And after tokenization, we will go to the next step in which we perform stop word removal and stemming. So stop word removal in this stage, what we do is we are going to remove the words which have little or no semantic weight. So words like and, or, then be, is, anything like that, this. So these words do not have much significance do not have much weight. You understand, right? So we cannot find out much information from such stop words. So that is why the best thing is to just simply remove them from your text so that you can focus on the main part, the main information that is being conveyed from your text data. And the next stage is stemming. So in stemming, we are trying to find out the root form of a word. So if you have words like running and runner, so all of them will be chopped off. The inflectional endings of the word will be chopped off, and you will get the word run from that. So these are some of the stages. So we can also call them as text normalization phase. So along with text preprocessing, we are also performing text normalization. And finally, we are going from the raw text to a set of preprocessed tokens. And these preprocessed tokens will be helpful for us to create good features. And these features will be then fed to your machine learning algorithm. Yeah, so the next stage is feature engineering. So like I said, now we have got our preprocessed tokens. The list of preprocessed tokens will now be used to form features. So feature engineering mainly focuses on converting the text into a vector. So this process is called as text vectorization. And for text vectorization, we have two popular techniques. So these are primitive techniques actually. Nowadays, we have a lot of advanced techniques, but you have to start from scratch. So let's see a bag of words model. And one more model that we have is TF-IDF model. So I'll go through both of them. But for our implementation, we are going to use bag of words, and I'm leaving you to TF-IDF. So you're free to experiment on your own, and you'll see how the accuracy is varying when you are switching from one feature vector to the other. Okay, so let's see bag of words. So it is a very popular and it is a simple method actually. So what we are doing is we are considering a word count as a feature. So it's simply the frequency of each and every word in your text, the corpus. And the more frequent a word is, the more important it might be. So we are relating the frequency to be the measure of importance for each and every word. So it is a good way to determine the significant words in your text, but it also has certain drawbacks, which we will see later. So here you have a corpus, and this corpus consists of 3 documents, D1, D2, and D3. And each of the document is actually a sentence here. So usually text documents are really lengthy, but for simplicity and for the purpose of understanding this concept, I have considered only single sentences. So you can see that if you make a collection of all the unique words in this corpus, in this collection of these 3 sentences, then we will get a vocabulary of size 15. So you can see down below, I have written the bag of word vector for document D1. So similar for to document D1, you can also construct bag of words vector for document D2 and D3. So first we have a set of vocabulary, And these vocabulary are all the collection of all the unique words in the corpus. And we are attaching the frequency to each and every vocabulary, each and every vocab word. So for A, we have 0 because in the first sentence, the lion is the king of the jungle. So you can see this. There is no A and decayed, endangered. So these words are not present in that sentence. So we are writing the term frequency to be zeros. From is, we are specifying that yes, it is present one time, then jungle is present once, king is present once, lifespans is not present in the first sentence D1, lion is present once, lions is not present, similar to that. So you can see the word the with a small t, so that is present twice in the sentence. So that is why we have written its frequency to be 2. So similar to that, we have a vocabulary, and as per the vocabulary, we are writing the frequencies for each of the respective documents in the corpus. So this is how the bag of words vector works, and it is a really good. It has been proven to be quite efficient for simple applications. So for our SMS spam classification, it works quite well. So you'll see shortly. Now we move to term frequency and inverse document frequency. So it is a statistical measure, and we are going to determine the importance of a word in the document. So it is a sort of, you can say, a weighted measure, because it ensures that the document specific frequent words, so the words which occur frequently across all the documents, the words which are not occurring across all the documents, but they are specific. So they are specific to one particular document. So suppose that a word is occurring only in document D1, but is not occurring across all the documents. Till D10, it is not occurring. So that particular word will have a higher weight. And the words which are common across the entire corpus, so words like, suppose your corpus is talking about a malware. Suppose we have a corpus in which we have documents which are related to malwares, and the word malware is occurring in each and every document across the entire corpus. So in that case, this word malware will have a low weight as compared to the other words. So what it does is that the unique words in the corpus will have a higher weight, and the words which are not so unique in the corpus, so they will be assigned a lower weight. So this is the formula for TF-IDF. And you can see that it's weight Wij, which is the TF-IDF weight for token I in document J. And TF-IJ is the term frequency, that is the number of occurrences of token I in document J. And we have n as the total number of documents. So in the logarithm, we have n divided by dfi. So dfi is the document frequency, so number of documents that contain token I. So that is why we call it as inverse document frequency, since we are dividing n by dfi. So the inverse document frequency is actually the logarithm of the total number of documents in a corpora divided by the number of documents containing that. So don't worry, you don't have to perform these computations on your own. We have libraries in scikit-learn which can perform this computation with a lot more efficiency. Okay, so before I go to the learning algorithms, I'll quickly show you the implementation of the data preparation part, and then we can study about the algorithm machine learning models that we are going to build. So I'll just reshare my screen. So I hope my Google Colab notebook is visible to all of you. And here, so you will have your own notebooks, so you can, if you want to implement side by side, you can do that. I'll also give you a little break of 2 to 5 minutes maybe, and you can run the code on your own, and you can share your doubts if you have any. After that, we will move to the part 2, which is deep learning models. So I hope you're familiar with Colab environment. If any one of you has not worked before, so first you'll have to connect your drive. So your data set is present in your drive, and here you have an icon. So you have the icon to mount your drive, and from there you can set the path to your data set wherever it is present within your drive. And here you will have the option to connect to drive. And here, if you want to use a GPU, you can do that. It's really free to use. But for machine learning models, we won't be requiring we won't be having any huge computation, so we can do it on. Okay, so. The first step is to load the data set. And here I've downloaded the data set from UCI Machine Learning Repository. And I've also attached the link here. So if you want, you can experiment with it on your own. And here is the paper, the research paper, which is associated with the data set. And it's a really good work. So if you are a research enthusiast, if you like to read papers, then you can go through it. Alternatively, what you can do is, it's really a fun implementing a given model in a research paper. So you can try to replicate the models present in the paper itself. You can follow the procedure listed there, and you'll also have the tools. So all the tools are available in Python. So you can readily understand the concepts first and then implement the models given in the paper. So replicating research papers is a really nice way to learn some concept. Okay, so the first step, what we have done is we have mentioned the path, which path where the data set is present. After that, we are using the Pandas library. So Pandas is a really powerful library present in Python, which helps us to work with data frames. And here I have loaded the data, and so the data is present as a binary file, but you can use the function read cs_csv to convert it into tabular format. And the class and the text were initially separated using a tab space. So you have to mention what the separator was, for both the class and the text. Otherwise, the data will not look good. It will not be loaded properly. So you can see we have one class column and the text column. And if you want to count the values of ham and spam labels, then you can see that most of the instances that we have, they are not spam, and only 747 instances are only spam data. So now we'll see the feature engineering part. So as I said, that we cannot feed raw data into machine learning algorithm, and we will need to pre-process the text. So the first step here is, so I have used only punctuation removal. So like I said, that there are a lot of steps involved in text pre-processing, from lower casing, then punctuation removal, stop word removal, stemming, but it also depends on your problem statement. So if you have a very large data and you are trying to capture the semantics, in that case, you may require to perform a lot more pre-processing. But for our data set, we are having really short sentences. And we do not require to perform much of the pre-processing. And you also should note that the pre-processing pipeline is in itself customizable. So we can always customize a pre-processing pipeline, and whatever steps are required in your in your application. So for example, we are going to perform SMS spam classification. So we are simply going to remove punctuations. So we are only going to take the first step of data pre-processing, that is punctuation removal. So I'm not going to perform stopword removal and stemming in this case, because we need those data. And also we are not going to remove numerics. So numbers, why? Because a lot of monetary information is given in the spam data, if you have seen. So the spam texts, whatever we have, they also mention about numbers and figures and money. So we need to preserve the numbers as well for this data. So for performing punctuation removal, I'm going to use the regular expressions library in Python. So this is the way first to get hold of all the punctuation marks, or all the punctuation marks which are available. So in string.punctuation, you have a whole collection of punctuations in English language. After that, we see, so as an example, I have displayed here that the eighth row of the data set. So here we have quite a lot of punctuation marks, exclamation marks. But if we are going to execute this statement, then the punctuation marks will get removed from the text. So that is how we perform the text cleaning process. So this is the code which I'll run. And this. So I missed out running some of the cells earlier. That is why there came an error. So now you can see that after punctuation removal, your pre-processed text is present in your data set. And the next step is to prepare the labels. So we have to encode the labels. We cannot have ham and spam as the labels of our data set. So for that purpose, we are going to use label encoder. We are going to assign numeric values to these labels. So let's do that. So what a label encoder does is it takes the classes and it assigns a numeric value to each of the classes. So we are going to transform the labels now. And for ham, that is the not spam class, we have zeros. And whenever it is spam, we have the label as 1. So your label encoding is done. After that, we are going to create the bag of words vectors. So for our purpose, we have used the count vectorizer. It's a really efficient library. It's present in sklearn. And so we have to first split the data set into train and test. So we are going to use train test split function present in sklearn. So here we are mentioning stratify equal to labels because we want to have a proportionate label distribution between the train and the test sets. And we are keeping the test size to be 30% and train size as 70%. Now we're going to create the count vectorizer. So we are mentioning max features equal to 2000. That is the size of the vocabulary that we are going to consider. So I'll just remove this. We are not going to consider stop words and SKs. Simple as that. Okay, so count vectorizer.fit. So also remember that whenever you are applying the fit function, you have to fit on the train set. And when you are transforming it into bag of words vectors, then you have to do it on train as well as the test set. So that is necessary because we are going to see how well your train set is able to generalize on other parts of the data. Okay, so that's done. And now we're going to see size of the bag of words vectors. So it is of size, vectors of size 2000, and we have 3900 vectors, and bag of words test. We have 1672 vectors, each of size 2000. Now this is ready. Okay, so now we're back with the presentation. Okay, so learning algorithms. So the first algorithm that we are going to experiment with is a decision tree. And in decision tree, it is a supervised learning algorithm. So it has both the instances as well as the labels of the corresponding classes. And the goal is to create a training model that will be used to predict the class or the value of the target variable. And it learns a simple decision rule. So a decision rule is basically making a decision at each and every node of the in internal nodes of the tree. And we are predicting a class label by starting from the root of the tree. So first is the root of the tree, and following the root, we are going to predict each and every class label associated. And we are going to compare the values of the root attribute with the records attribute. And we follow the branch corresponding to the value and jump to the next node. So you'll understand it more properly if you see an example. Okay, so this example is this decision tree actually classifies Saturday mornings according to whether they are suitable for playing tennis or not. So this is a really popular decision tree that is used in most of our machine learning classes. So here we have Outlook, and Outlook is the root node. And from the root, you can see the branches. So if it is sunny, then we are going to check whether humidity is there or not. And if humidity is high, then it is not suitable for playing tennis. If humidity is normal, then it is suitable for playing tennis. So that is how we are going to make our decisions. And in our day-to-day lives as well, this is how we make our own decisions. It's not just restricted to this algorithm of decision tree. Even if we want to go out and play, we will definitely see the weather. And this is how we will judge whether it is suitable or not. So a similar kind of concept is applied to your decision tree algorithm. So it is a really simple model, and that's all. And it is mainly, we say that it represents a disjunction of conjunctions of constraints on the attribute values of instances. So each path from the tree root to a leaf will correspond to a conjunction of attribute tests, and the tree itself to a disjunction of these conjunctions. Okay. So now we will also see one more algorithm, and then we will see the implementation. So this is the multinomial knife Bayes algorithm, and it is also a supervised algorithm, and it is mostly used for text classification, for spam filtering, in sentiment analysis. So it works really well with text data. And main concept involved with naive Bayes is that the occurrence of one feature does not affect the probability of occurrence of the other feature. So these features are independent of each other, but in reality, this is not always the case. That is why naive Bayes does not perform well for all cases, but for small data sets, it is quite robust. It is also easy to implement. It works really quick and it is accurate. And in this case, it will consider a feature vector. In our case, we have designed a bag of words feature vector, and it will treat all the words equally, regardless of how they are placed. So this one is an example. So the above formula is the Bayes rule, which is the heart of this algorithm. And suppose we are having some words. So dear, friend, lunch, and money. So these 4 words, and we want to check their occurrence in messages. So we are going to calculate the probability of seeing each word, given that the message was not spam. So if the message is normal, what is the probability that the word dear occurs? So here, so this was an example, and from there we computed that it was 0.47. So this is the way multinomial naive Bayes works. It will find the probability of seeing each and every word in the corpus. And this is how it assigns the probabilities. Similar computation will be done for messages which are spam. And based on these computations, it will decide whether a given message is spam or not spam. So each and every word in each of the documents will be analyzed to come to a conclusion. So we'll see the implementation now. So the first one is the decision tree classifier. And here we have created an instance of decision tree, and we are fitting the bag of words model that we have and the labels that we got. After that, we are collecting the predictions for the test data. And if we want to check the performance of a classifier, we can use confusion matrix, the accuracy score, and classification report to see the class-wise accuracies. So a confusion matrix actually tells us the per class performance of your algorithm. In this case, for not spam, that is ham class, we have 1,419 labels that were classified accurately and 29 labels that were classified inaccurately. Similarly, we can see that for the spam class, we have 192 instances that were classified accurately. So you have to see the diagonal elements for accuracy, for those classes that were classified accurately. And here we have our accuracy score, which is 96.35%. From here, you can also analyze the performance, the relative performance of both the classes as the precision recall F1 score. Okay. So now we are going to see the cross-validation score. Sorry. I think some libraries are missing from here. So yeah, we got 96.17% accuracy. After that, we'll run this cell. So our cross-validation accuracy is 95.6%. So cross-validation accuracy, as in we have 10-fold cross-validation. So your data set will be divided into 10 folds. And then the training part will be, the model will be run that many times and an average score will come. So this gives us a more appropriate view of our model, how well it is performing for a specific problem. Now we'll see the multinomial naive Bayes. We can create an instance of the naive Bayes model using multinomial NB here. So in NB, we have our model, then model.fit. We will do back of words train and Y train. A similar process is followed. Now you can see that it performed really well in case of multinomial naive Bayes. We got 98.56% accuracy. So this machine learning model performs really well with test data, especially when your text data is small in size. So in that case, it is able to perform quite well in a robust manner, and it may even compete with higher complexity models. So this accuracy will even be competing with the accuracy of attained using neural networks, using a deep learning model. So it achieves that kind of high accuracy with text data. So if you have any text-based project and the text instances are small in size, then you can always use multinomial naive Bayes. I'm sure that it will always give really good results. And let's see the cross-validation score. So it is around 97.9. So we can round it off to 98%. All right. So with multinomial naive Bayes, we got around 98% accuracy. And with decision tree, we got 95.6% accuracy. So here we finished our machine learning part 1. And now we will start our deep learning model part, but I'll give you a break of 5 minutes around. Yeah, that would be good. So you can, I shared the notebook with you in the chat box. So you can have a look at it. And if anyone has any doubts in part 1, then feel free, you can use the chat box and you can communicate your doubts so that within these 5 minutes, I can address your issues. And next, we will start with the deep learning part. Okay. If anyone wants, I'll again share it. Okay, so please let me know if there are any doubts anywhere. Even in implementation, if you are facing issues with Colab, please let me know. I could help you out right now, and then we can start with deep learning. So I'm again sharing the folder. You please go through that. And it is the first notebook, part 1. And if there are any doubts or any questions related to the concepts that we discussed right now, you can type it out in the chat box and address your queries. Everyone, please feel free to ask your questions. I'll address all your doubts, and you can even unmute yourself in case you want to elaborate your question. And please go through the code segment. If any concept is still unclear, then do ask me. I'll go through that again. Or we'll start the next part in 1 or 2 minutes. Hi, Nani. So count vectorizer is being used to create the bag of words vectors. So at the starting of the session, I told you that we will be converting those text documents into numeric representations. And as for the numeric presentations, we are using the bag of words model. And your bag of words model is consists of essentially the frequencies assigned to each of the words in your document. So what count vectorizer does is that it is simply creating the bag of words vectors for each of the text document instance in your data set. So once you are getting the bag of words vectors using count vectorizer, after that we can apply the machine learning models on these features that we have got. So I hope I was able to clear your doubt. Okay. Okay, all right. Do we have any more questions, or else I'll begin part 2? Okay. Okay, then we'll start with the deep learning models now. So we all know that how powerful deep learning models are and how they are being used in almost every sphere of life. So deep learning is actually able to give us a really good accuracy, and they are able to find hidden patterns from the data set, from within the data set. And some of the popular deep learning algorithms used nowadays are CNNs, RNNs, LSTMs, GRUs, and now we also have generative adversarial networks. So these are performing quite well, and they are being extensively used in research. So that is why an insight into deep learning and how we can perform natural language processing using deep learning is quite important now. So let's begin the part 2 of the session. So the first step is tokenization. So we are going to encode the sentences into numbers. So suppose we have 2 sentences, I love my dog and I love my cat. So each of the words in the sentence will be assigned a numeric code. So this is the encoding part. So we will represent the sentence, I love my dog, as a sequence of tokens, which is 1, 2, 3, and 4. And the next sentence, I love my cat. So we need to differentiate between 2 tokens, dog and cat. So we will represent the second sentence as 1, 2, 3, and 5. So you can also see that 1, 2, 3, 4 and 1, 2, 3, 5. So this has some level of similarity as well. And we are also able to distinguish between dog and cat using different tokens. So there are some steps in TensorFlow. So first we are going to perform tokenization. After that, we are going to create sequences. We are also going to pad the sequences. So padding step is to set a definite length to all the sequences that we have got. Suppose that if we have a sentence, I love my dog, and the second sentence is not just 4 tokens, but I am going on a morning walk. So that is a longer sentence. So we want all the sentences to have the same length. So in that case, we are going to perform padding. And after we have padded the sentences, we are going to perform word embedding. So so using these word embeddings, we are going to first tokenize the words. We are turning them into numbers. And after that, we are going to take these numbers and we are going to establish some sentiment from them so that we can begin to classify and then data predict the text. So embeddings can be used to represent the semantics of the word. And so instead of the word just being a number. So in earlier cases, we saw the words were, we were using features like Vectorizer, in which we are only giving the frequency of each of the words in the vocabulary. And these are the numbers that are representing the words. So now we are diving deeper. So we are going towards a class of techniques where all the individual words will be represented as real valued vectors. So these vectors will be in a predefined vector space. So for that purpose, instead of the word just being a number, so now it is going to be like a vector in an n-dimensional space. And you may have heard about pre-trained word embeddings, if anyone has heard about it. So nowadays, a lot of pre-trained word embeddings are also available, and we can also use them to capture the semantics much more efficiently. And the words as well as all the associated words are clustered as vectors in a multi-dimensional space. So here is an example. So you can see that we have the words king, queen, man, and woman. So the distance between the vectors king and queen, that is the same distance as the distance between man and woman. What we can see, what we can conclude from the first diagram is that the relationship between king and queen is the same as the relationship between the words man and woman. Similarly, we can see verb tense. So walking and walked, and as similar to swimming and swam. So in that way, word embeddings help us to understand the relationship between the words, and they are helpful to capture a lot more semantics within our corpus. So they are quite efficient, and they are under research right now. A lot of word embeddings are being developed, which are really performing good. And they are even in industrial use right now for industrial NLP applications. So let's see the word embeddings in use. So I'll switch to the implementation again. So, first, I'm going to go through some of the basic concepts that will come into use while you're going to use the word embeddings. So like I said, first we are going to perform tokenization. After that, we are going to create the sequences. And lastly, we are going to pad those sequences. So here we have the 3 sentences, and if I run them. So on running them, first, we are going to use a tokenizer. So this is available in TensorFlow. So tokenizer, number of words, 100. So that is the maximum limit of words that we are going to feed into the tokenizer. We use the function fit on text. So what the collection of sentences that we have, we are going to pass it as the parameter to the function fit on text. And using this function, we will create our own vocabulary. So it will find out all the words, unique words in the collection of sentences, and it will also give us the word index. So upon printing the word index, you can see the words are assigned a unique token. So the encoding has been done now. So the word love has been assigned a token 1, then mine 2, I 3. And one thing you may notice that here we had a token, dog and exclamation, but the tokenizer available in TensorFlow is smart enough to understand that the exclamation does not create a different token, and instead we are only having one single token as dog. So here we have performed a tokenization, and now we have another sentence collection, and we are going to create the sequences from them. So if we have sequences are created using the text to sequences method function. So you may also notice that I have created an OOV token equal to OOV. So this is used to represent the out of vocabulary tokens. So suppose that we have this collection of sentences, but we are required to encode another collection of sentences based on the vocabulary that is learned using this corpus. In that case, what happens is that those out of vocabulary words that may be present in the test sequence of sentences, they may not be present in this particular corpus. So we need something to represent those words which are outside the vocabulary of this train sentences. So this is my train sentence. And the words which are not available in this set of sentences, if we are going to tokenize those words, then we are going to use the out of vocabulary token. Again, we are using the fit on text method. Then we are using text to sequences function to convert all our sentences into a list of tokens. So these are the sequences. Lastly, we are padding the sequences. So padding is required to have a uniform length of sequences, and padding is usually done using zeros, and it is I think it is yeah. So zeros are appearing at the beginning of the sentence. So this is pre-padding. And here we have assigned a max length to be 5. However, if you wish, you can change it. So if we have max length 10, then you can run it again. Yeah. So this is how your padded sequences will look like. And these are the sequences. So the first sentence that we had was, I love my dog. If we go to these sequences and use the word index, then you can get the original sentence back. So five is represented, I is represented using the token 5. So I love, which is 3, my 2, and dog 4. So that is why we have 5, 3, 2, 4. So in this way, we are representing the sentences. So again, if we go to the next sentence, I love my cat. So we have 5, 3, 2, which is I here. Then again, we have love, 5, 3. Then we have 2, my, and we have cat, which is given by the token 7. So I love my cat. So that is the way we have created the sequences. So sentence encoding is done initially in this manner. And after that, we have attained the padded sequences. And these padded sequences will be used to create the embedding. So this was the, so we experimented on a simple data set, a simple collection of sentences actually. And now we are going to work on our own data set. Okay, and the usage of out of vocabulary tokens as well. So here, suppose we have two sentences. I really love my dog. My dog loves my manatee. And the word vanity is not available in our corpus, but you have seen that the OOV token is represented by 1. So when we are encoding this just sequence, you can see 24121 for the sentence, my dog loves my manatee. And you can see the words which are out of vocabulary, they are represented by the token 1. So that is the usage of out of vocabulary OOV token. So it helps us to maintain our tokenization pipeline, and as well as uh, no tokens will be gone missing. So if you are not mentioning the OOV token, then it may be possible that the tokenizer may not detect anything at all. So that is why it is advisable to you always use the OOV token for keepsake. Okay, so now we are going forward for implementation. So we have defined the path of the data set. We load the data set. So it's the same procedure as above, the earlier part 1. And you can see the first instance of the data set. So we have the class ham and the text is here. So the initial setup, we have to import the necessary libraries, and we have to perform label encoding as well. So now we have all our labels in this variable. So we have transformed all the labels into zeros and ones, since we have only 2 classes. After that, we have set our vocabulary size to be 1000 and embedding size of 16, max length of 120. We are going to perform post truncation and post padding. Post padding because in that we want to add the zeros at the end of the sentences, so as to get to the maximum length, which is 120. And we also have defined our out of vocabulary token. So the next case is, okay, so this is just exploring the data. And we are again using 70-30 split for our train and test sets. So you can see we have train 3,900, and for validation sentences, we have 1,672. So this is the tokenizer step. So this is how it appears. But after padding, you may notice some sparseness, a lot of zeros here, but that is how it works. And because there may be some sentences which are longer in length. So we need to preserve them as well as maintain some uniformity. That is why we have to go through this step. We also prepare our validation sequences. All right, now we are going to work on our model. So you can see the first layer that we have, this is the embedding layer. So in the embedding layer, we have mentioned our vocab size, embedding dimension, and input length equal to the max length. And we have a global average pooling layer as well. And the dense layer consisting of 24 units along the activation ReLU. And the last layer, which is dense layer, here, activation softmax. Then we are going to compile it. So we are going to use sparse categorical cross entropy and optimizer at a matrix accuracy. So this is our model. And we are going to, okay, so for purpose of simplicity, let's have 5 epochs. And here we have train padded, X train, which is X train, Y train, number of epochs, validation data, which we have given. And we have set verbose equal to 1 because we want to see the results at each and every step. So, maybe I just forgot to execute one of the cells earlier. So that is why I'm having one error. Okay, right. So we have, with 5 epochs, we were able to get an accuracy of around 85%. So let's increase the number of epochs since the model is not that complex. So let's increase it to 15. And yes, so I hope you remember how a multinomial knife base performed. So it was able to achieve around 98% accuracy. And I also told you that multinomial knife base performs really well with a small amount of data, and it is able to achieve accuracy at par with any of the complex models. So here is the testimony. You can see the accuracy achieved here is 98.54%, and the validation accuracy is 98.03%. So we can now conclude that these two perform really well, and a simple algorithm as multinomial knife base is also able to spot the patterns within the data. And if we want to explore this model more, we can plot the valid accuracy graph and loss graphs. So here you can see as epochs on x-axis, the accuracy on the y-axis. And you can observe that there is a certain degree of overfitting at this point where your validation accuracy was greater than the train accuracy up to this point. After that, the train accuracy becomes greater and the validation accuracy decreases a bit. So here you can see that there is some degree of overfitting. So similarly, we also have the loss curves. So you can explore different models, you can explore different problem statements, and you can work on similar problem statements with different data. You can apply these techniques in your own projects. So this is all the implementation that I wanted to share with you all. So if you have any questions, then please feel free to point out.
Ma'am, could you please scroll up? What was the last layer of your model?
Yes, yes.
Ma'am, why are
Yeah.
we using activation softmax here? I mean,
We are
yeah, I
we are
mean, the
going.
classification is binary, isn't it? Spam or ham.
We can also use softmax, so it won't make any difference. We can also use, if you want, you can use sigmoid. It works in the similar manner in case of binary classification, but we can also use softmax. It works the same way for both. So specifically for binary classification tasks, when you have only two classes, so softmax will also work and sigmoid will also work.
And what does these six output nodes indicate? What are these? What does this six signify in the last layer?
So what happened is that, so here when we were transforming the labels, so we have not just transformed the sentences, we have also transformed the labels in some manner. So that is why we have to use, so it's like that. So I have to explain it using the diagrams. I have not plotted the model, but if I would have, then I could explain it or explain it properly. Any more questions?
No, ma'am. Thank you.
Okay, so someone is asking me to share the file. Anyone, if anyone has any questions, then please feel free to ask. Hello, Shivam. Yes, you pointed out that was an error, I think. It was not six. I had actually transformed the labels earlier. So there is a mechanism of label transformation as well. So we can encode the labels in different format. So if we have two labels, then I was earlier encoding the labels ham and spam into in a different manner. But lately I just changed my code and I forgot to change my last layer. So as you pointed out, in the last layer dense, we will specify two. Okay, so we will have two nodes in the dense layer. Activation will be softmax because we are going to identify two classes. So we have two classes, ham and spam. So we will have two nodes in the last layer. However, if you are using a sigmoid, then I think you will be using one node in the dense layer. So that is the change that you have to make in case you have to use a sigmoid activation function. So I hope I'm able to clear your doubt.
Yes, ma'am. Thank you.
And thanks for pointing out. Do we have any question? I have shared the code with you all. So you can go through the entire code file, and if you have any doubts, you may comment over there. So there is also a comment section in the notebooks. So you can run the entire code on your own. And I have also shared the data set in the Google Drive folder. So you can copy all of the files to your own drive and you can implement it simply. If you don't have any questions, then we can end this session. Thank you, everyone. And I hope you all are staying safe and staying comfortably at home, and keep learning and keep exploring different areas in AI. And that's all for today. Signing off. Thank you, everyone.